Good day. This is a small addendum where we will touch upon some of the core concepts in Bayesian hypothesis testing. Let us start by recalling the fundamental difference between classical estimation theory and Bayesian estimation theory. In classical estimation, the parameters that we wanted to estimate were unknown deterministic creatures, right? So we didn't express any preference over some values of the parameters relative to others, right? In contrast, in Bayesian estimation, we modeled the parameters as random variables, and we introduced prior distributions on them, right? That had the impact of biasing the estimates towards what our prior information was dictating, right? In detection theory, there is also a similar distinction. Note that in the previous lectures, we just we didn't have any probability. We didn't assign any probability to the hypothesis, right? So we didn't express any preference in for H0 or H1, right? So we were sort of neutral. However, in many situations, one knows, for instance, what is the relative frequency of each hypothesis, right? So, for example, in communications, we typically know that the probability of a bit being zero is roughly the same as the probability of it being 1. And this is because we use what we call source coders, right, which compress the information to reduce the number of bits to be transmitted. And these source coders therefore try to maximize a metric that is called entropy, right? Because that is the optimal way of compressing information. But in other areas or disciplines, it is also very common to know these probabilities, right? So we typically know what a fraction of the population has a certain disease, right? And that could be used to make decisions on the procedure to follow with a certain patient, right? However, the notion of a probability on a hypothesis doesn't really make sense in other contexts. So, for example, in radar, it wouldn't really, make sense to talk about the probability of that there is an enemy aircraft over us, right? So, how would you define that probability, right? Or even, for instance, in emergency management, so or in general detecting some emergency situation, right? So we have a smoke detector in our room. It is not for sure using any prior probability that there's a fire, right? What is the probability that there is a fire, right? So if it is testing, running a hypothesis test every millisecond, right? What is the probability that in one of those time slots there is a fire, right? So that is not looking at prior probabilities is only motivated in certain cases. And a very important advantage of introducing prior probabilities for the hypothesis is that we can talk about other very interesting performance metrics. So this is the case, for instance, of the probability of error, which is directly the probability that our decision is different from the true hypothesis. So it doesn't matter whether this is H1 and this is H0 or vice versa, right? This is in contrast to the framework for non-Bayesian detection that we saw in the previous lectures. So let us express this probability of error in a more convenient form. We can start by decomposing this probability in this way. We just use the fact that the probability of the union of these joint events equals the sum of their probabilities, right? So here in this case, we separate this into two cases. One is where the true hypothesis is H0, and the other is when it is H1. And now one can apply the definition of conditional probability, and therefore this reads as this the probability that the true hypothesis is H0 times the probability of making a mistake when the true hypothesis is H0, right? And the second term is the same, but for H1, right? So this is like the probability of false alarm, right? Because this is the same as saying a probability of this is like deciding H1, right? Because H2 is H0, and this will be like the probability of misdetection. So this can be even expressed in this way. And the good news is that an estimate detector that minimizes the probability of error generally exists, right? So and another interesting fact is that its test statistic is given by the likelihood ratio in the same way as the test statistic of the most powerful test as dictated by the Neyman-Pearson theorem. The difference with that theorem is that now the threshold is given by this fraction between the prior probabilities of the hypothesis, right? So in the Neyman-Pearson framework, we had to choose this threshold to attain a certain probability of false alarm. And that is sometimes problematic because that involves computing the probability of false alarm and solving, so expressing it in terms of the threshold and then solving that equation for the threshold. And that is often not tractable analytically, and therefore one needs to use something like Monte Carlo. But here it is it is easier, right? Because these probabilities are given to us. So we have here a very simple detector. Or if the test is, let's say, it's composite, then one can assign priors to the unknown parameters following the philosophy in Bayesian estimation as well. So, so this is just a very quick introduction to minimum probability of error detectors. Another important strength of the Bayesian approach to hypothesis testing is its ability to capture the different costs and that different kinds of errors may have. So this is easy to understand if we think, for example, of the case where we need to determine whether a patient has or not a certain disease in order to decide whether we start or not a treatment, right? So if, for example, the patient doesn't have cancer, but we determine that she or he has it, then we would be starting a chemotherapy treatment in a totally unnecessary fashion. So this, of course, has a negative impact for the health of the patient, but the cost is much smaller than the cost of the other kind of error, which would be determining that the patient doesn't have cancer when she or he actually has it, right? Because in that case we wouldn't be starting a treatment, and her or his life would be compromised, right? So let us introduce this notation. This function L will be used to denote the cost of deciding H and J when Hi is true. With such a definition, it is natural to introduce this performance metric, which is called the base risk, and is just the expectation of this loss, right? So note that this expectation runs across realizations of the data, but also across hypotheses, right? So by the definition of expectation, this is just the weighted sum of the loss of all possible pairs of hypotheses and decisions, right? So note that in general we will have also, or we can accommodate a loss even for correct decisions, right? Although oftentimes the loss when Hi equals Hj will be 0, right? And by using the definition of conditional probability, and this can be written in this way. So this is weighted by the probability of each hypothesis and by the probability of error corresponding to this decision rule when a hypothesis Hi is true. And it can be shown that the decision rule given by this expression minimizes this the base risk. So again, we have here a likelihood ratio compared with a threshold, right? And this one generalizes the expression that we saw in the previous slide for the minimum probability of error and detector, right? So there we just had these two terms for the definition of for the value of the threshold. Now we have also the value of the loss for these different combinations of true hypothesis and decision, right? So note that if we set the loss associated with with a correct decision equal to 0, right? So this becomes 0 and this becomes 0. And if we set the cost of both kinds of errors to be the same, then this quotient here becomes 1, and we recover the minimum probability of error detector as a special case of this one. So the minimum base risk detector generalizes the other one. Note that this is not the first time we look at the base risk. So when we discussed maximum a posteriori estimators, we started by generalizing the VMSE to accommodate different costs depending on the direction of the estimation error. And the expression was pretty similar to this one, right? So instead of having the true hypothesis here, we would have the true value of the parameter, and instead of having here the output of the detector, we would have the estimate. So essentially this notion of base risk is common for estimation and detection. So let us wrap up. In this short video, we introduced the basic concepts in the theory of Bayesian hypothesis testing, which hinges on assigning prior probabilities to the hypothesis. This allowed us to introduce two new performance metrics, namely the probability of error and the base risk. The probability of error is sort of the weighted sum of the probability of false alarm and probability of misdetection weighted by the probabilities of each hypothesis. And the base risk is a generalization that allows us to accommodate the different costs that different kinds of errors may have. We also presented the optimal tests according to these criteria, and it is remarkable to note that their test statistics were, in both cases, the likelihood ratio that we know from the previous lectures. So this brings us to the end of the lecture and therefore to the end of the course. Now we can just list a few possible next steps. One of them would be, of course, practice. So this discipline is learned by practicing with a pen and a paper, also with a computer. We need to do many experiments. We also need to try to work out the derivations and everything that helps us with our understanding. We didn't look at any example of these detectors, so that should also be done. Besides the estimators and detectors that we looked at here, such as the MVU, the blue, maximum likelihood, least squares, now then we saw the most powerful test, the uniformly most powerful test, the minimum base risk detector, and so on. Besides those, there are many other possible criteria that we didn't have time to cover, but now you have the background necessary to read about them and use them whenever needed. We also we didn't have time to look at the multiple hypothesis testing. We only considered binary hypothesis testing, but the case where more than two hypotheses need to be tested is also very important and widely used in or shows up very frequently in practice. And throughout the course, we extensively made use of probabilistic models for the data, but there are also families of methods that learn the distribution from the data itself. Of course, those approaches need much more data, right? So in practice, we will be using something in between, something perhaps some data-driven approach that also accommodates some model information or the other way around. Also, we assume that the data and the parameters that we wanted to estimate were vectors, right? This, I mean, of course, applies in the same way. All these approaches would apply in the same way for estimating matrices or tensors or any object in a finite dimensional space, right? But estimating functions is something fundamentally different. And the reason is that functions live in infinitely dimensional spaces, right? And therefore, this is, of course, something that is very convenient to learn, that would help us with the doing what they call non-parametric regression or non-parametric estimation, which finds many applications in practice. Another direction where we haven't moved was unsupervised learning. So there is of course the need to sometimes just understand the data, perhaps cluster the data into categories and reduce the dimensionality, things like that. So there are operations performed by data scientists every day, and we also didn't have time to cover. So for this family of for these three bullets, students may benefit from taking a course in machine learning and study their kernel-based learning, deep learning, I mean, in general, neural networks, right, and so on, right. But as I said, this course has a limited scope, but at least I hope that the main ideas, the fundamentals, are now clear, and then learning these sort of techniques should be pretty easy for a student that has mastered the contents of this course. So that's it. Thank you very much for your attention, and I'll see you next time.